Hello and welcome to today's lesson, which is on partitioning a line segment based on a ratio. And that makes this first example, if you want to take a moment to read through it, if you haven't already, you can pause me. But it makes that first example look a little out of place, because this really has nothing to do with line segments. So we're looking at an algebraic example in a geometric section. That's okay, algebra is quite woven into geometry. That's why you're supposed to pass it before you take geometry. But what this problem is saying is that, kind of in between the lines, there's three parts of this business that's Radke, we all see that, and there's two parts of this business that's Santana's responsibility, for good or bad, better or worse. But the important part that gets overlooked a lot in these partitioning problems is that there are 5 parts total. That is a key ingredient in this entree. Because what that does is it allows us to write a proportion based on Radke's part out of a total. For instance, Radke owns 3 parts out of 5 total, so he should get, Radke's earnings should get whatever part of the total $200,000. See, that $200K is a total. It's split between the two of them, and that's why we need the number of parts total. If you cross multiply here, you get 600 grand equals 5R, and if you divide away the 5, you get 120,000 for Radke. Therefore, Santana's going to get the rest, which would be the other 80,000, because there's supposed to be a total of 200 grand. Well, we have a little bit of vocabulary to introduce in this next problem. The idea of a directed line segment. A directed line segment varies from a regular line segment in the following way. Regular line segment doesn't matter if I call it CD or DC. Directed line segment, if it says start with point C, then the only name for this thing is CD. And by using a directed line segment, it'll help us figure out which side or which endpoint our partitioning point is supposed to be closer to. So it removes that guessing game. The key here is not necessarily how many parts each segment gets, although that's important. The real key is the fact that there are 7 total parts. Like if I could chop this segment into 7 equal pieces, 1, 2, 3, 4, 5, 6, 7, and give 5 of them to CP, and then the other 2 to D, I'd be done. And that's about where my answer is going to be, right in there. Now I'm going to use math to figure out exactly where it is, but that's the idea behind this problem. So we've got 7 total parts, and it just so happens, measuring my segment gives me 21 inches, which is ever convenient because it divides nicely by 7. Now when you do your measurement divided by 7, you will probably get a decimal. That's okay, because decimals are numbers too. But for me, I get 3 inches per part. So if segment CP gets 5 of those parts, 5 of those 3-inch parts, that means it's supposed to be 15 inches long. So I'm going to take a ruler, I'm going to measure, starting at point C, I'm going to measure 15 inches. And that's where I'm going to place my partitioning point P. Done. Now most of the time on these kind of problems, they will give you not something you have to measure with a ruler, but rather something on a coordinate plane. I didn't label my endpoints. Shame on me. C, D. It's a directed line segment, meaning you're starting at C and going across toward D. Well, first it says to find the midpoint of CD. That's easy enough. To get a midpoint, you take the x value of the midpoint, I'll call it x sub m, is just the average of the 2 x values in the problem. So -4 and -2 are my x values. To average them out in a 1-to-1 ratio, which is what a midpoint is, you just divide it by 2, because they each have 1 part So there's 2 parts total. You get negative 6 over 2, which is negative 3. The y value of the midpoint, you use the y values in the ordered pairs, 8 and negative 1. Average them out, means add them up and divide them by 2. 7 halves is what you get, which is 3.5. So your midpoint is at negative 3, 3.5. That's my partitioning point. Midpoints work by partitioning the segment in a 1-to-1 ratio. Now what we're going to do in part B is a little more complicated. Instead of a 1-to-1 ratio, we're going to be using a 2-to-1 ratio. Let me give you a little bit of a background as to how we can do this. The x-coordinate of the partitioning point, much like with midpoint, is going to come from a fraction where you add things at the top and you divide by something. What we're going to do is we're going to take the first x value, so in this case negative 4. Now at a midpoint we just say, well, that gets 1 share. But when you're not partitioning in a 1-to-1 ratio, you need to multiply this by something. We're going to multiply it by the weight of x2. I'll explain that in a second. Then we're going to take the other x value and we're going to multiply it by the weight of the first. Underneath, we're going to divide by the addition, the sum of the 2 weights, which is just like we did before. The last problem, we had 5 parts for one segment and 2 parts for the other, so we had 7 parts total. You're really just adding up the total number of parts. In this case, there's 2 shares for one part of the segment and 1 share for the other. So we're going to get 3 as our denominator because there's 3 total parts. When I go to plug in numbers here, x sub 1 is simply the first x value, negative 4. We're going to multiply that by the other x value's weight. The other x value has a weight of 1 in this ratio, so 1 goes in for w sub 2. X sub 2 is the second x value, which is negative 2. I'm going to multiply that by the weight of the first the first partition, which is 2. Divide all that by the sum of the weights, the total number of parts, which is 2 plus 1, which is 3. If you do the math on this, you get negative 4 minus 4 over 3, so negative 8 over 3, which is negative 2 2/3. Writing it as a mixed number is going to help me figure out where it is on the graph. I'm going to write that down so I can erase some of this and get some more workspace. So my x partitioning coordinate is negative 2 2/3. Now let's tackle the y partitioning coordinate, and frankly, it's going to be the same logic here. We're going to start with the first y value, multiply it by the weight of the second, and add on, go the other way with it. The second y value times the weight of the first, and we're going to divide the whole thing by 3 again. So the sum of the weights. So for us, the first y value is 8. The second weight is 1. The second y value is negative 1. And the first weight is 2. The sum of the weights, again, is 2 plus 1, which is 3. So you get 8 minus 2 for your numerator, 3 for the bottom, and your y value is 2. So this partitioning point that we need here, starting at point C and going to point D, is at negative 2 2/3, comma 2. If we plot that, we should be on this segment, or else we goofed. So -2 2/3, comma 2 would be right here. That is my point P. That means for every, that means this segment will be twice the length of this bottom segment. Hence the 2-to-1 ratio.